Okay, so switching gears from our last unit here, we're going to start looking at triangles. Before we get too far into it, there's a few things you need to try and remember from previous years. So first thing you may remember, some of the angles in a triangle, all three of them have to add up to 180 degrees. That's for any triangle. Supplementary angles, such as the ones you see on the right, they look like angles along a straight line. So you've got two angles here, 150 degrees and x. These supplementary angles have to add to 180 degrees. So that would mean that x in this case would have to be 30 degrees. So those can add together to 180. Some other things that you saw in previous grades, the Z pattern, also known as the alternate angle theorem. And the situation that you're going to have here is if you have two lines that are parallel here, what you may remember is that in this situation these two inside angles here are going to be the same. You also saw an F pattern back in grade 9, and that one told you that if you had two parallel lines right here, that the two angles here inside that F, so to speak, would be the same. Okay, so that's also known as the corresponding angle theorem. Okay, so with that in mind, something else that you may have seen back in middle school, and if you don't remember it, not too big a deal, is just the idea of congruent triangles and what congruent means. So, for example, if you have two triangles and we're calling them congruent, we are essentially saying that they are the same in every way. They have the exact same shape, the exact same size, all the corresponding angles and sides are going to be the same with each other. The only thing different about them is the name. So in this case, we have triangle ABC, triangle DEF, but aside from that name, everything about them is the same. So the symbol that we use for congruence is this one right here, the little equal sign with a tilde on top. So that symbol means congruent. And again, just to recap what this means, if these two triangles are congruent, then every corresponding side is going to be the same. So AB and DE will be the same length, BC and EF will be the same, and AC and DF. Looking at corresponding angles, angle A and angle D are the same, angle B and angle E are the same, and then we have angle C and angle F. Okay, notice that when we name the triangle ABCDEF, we name it in the same order. So A down to left to B across to C, similar in order for DEF, so it's very easy to pick off the corresponding sides and angles just by looking at this statement right here. We don't necessarily have to look at a picture. So the other thing that you may remember looking at when you're naming an angle, you might call, if you're looking to find angle A, you might call it BAC. Okay, naming all three vertices that make the angle, with the middle one here being the angle that you're actually looking at. Now, just for the sake of making things easier on ourselves, if you mean angle A here, I'm not going to require that you write angle BAC, just write angle A. Similarly up here, instead of angle EDF, we're just going to write angle D, just to make things easier on ourselves. Okay, so that was the whole idea of congruent triangles. So what I'm going to show you now are these two triangles, which are clearly not congruent, because they're definitely different sizes. One is clearly larger than the other, but they do have some things in common. Okay, we have, if you look, all the corresponding angles are the same. We've got a 50-degree angle, a 100-degree angle, a 30-degree angle in each. So we can say that all the corresponding angles are equal. Okay, furthermore, if I look at the corresponding sides, I have a ruler on here. You might find it easier to use the page in front of you and your own ruler to measure these lengths, but here on this ruler, I can measure a distance of, if I'm measuring this bottom side AC, it looks like I have a measurement of about 14.6 units. So I'm just going to put that in over here. AC would be 14.6. And I'm going to measure that corresponding side on the other triangle. Okay, and again, measuring this bottom right here, it looks like it's about 7.3. So XY is going to be 7.3. Now, taking a quick look at that, you might notice that 14.6 is exactly twice as large as 7.3. So that ratio between the corresponding sides is going to be 2. AC is twice as large as XY. And I'll let you do this for yourself with the other sides taking out a ruler. But you guys see that that same ratio exists for every pair of corresponding sides, meaning that AB over here will be twice as large as XZ, and BC will be twice as large as ZY. So what we say in this case is that there's a scale factor of 2 between these two triangles, meaning the corresponding sides of the larger triangle are twice as large as ones from the smaller triangle, and what we can say is that the corresponding sides in these triangles are proportional to each other. Okay, so that's what's going on with these two triangles. So while these two triangles are not congruent, we do have a special name for them when these relationships do exist between them, and that is that they're going to be called similar triangles. So again, with any similar triangles, any corresponding angle that you have between the two triangles are going to be the same, and the ratio of the corresponding sides will be equal, or you can say it as the corresponding sides are proportional to each other. So you have an example down here of two similar triangles. Okay, we have a similarity statement here that says we have triangle ABC being similar to triangle PQR. So the sign for similar is just the little tilde. Okay, and again, meaning the corresponding angles are the same, so angle A and angle P are the same, B and Q are the same, and then again, C and R are the same. The only difference now, comparing to congruent triangles now, is that we have corresponding sides not being the same, but again, proportional to each other. So there's going to be some sort of scale factor that exists between the corresponding sides, PQ and AB, and that same ratio exists between these two sides and these two sides. So the other thing that that might be a little bit new, just as a convention for naming sides, instead of always naming them by saying the two vertices that make up the side, convention tells us if we're going to label the sides of a triangle, they are usually called by the same letter as the angle across from it, and usually with a lowercase. So across from angle C here, we're going to have side little c. Across from A, we have little n, and across from B, we have side little b. So similarly here, we have side P, side Q, and side R. And that's just a convention. That's going to help us a lot going forward and move into trigonometry, so it might be worth getting used to now. So another way you could write this proportionality statement over here is just using the alternate side names there. Okay, last little definition to look at here is looking at what we call the scale factor, and we saw it back last slide with a scale factor of 2, and it's just the value of the ratio of the corresponding side lengths. By convention, we just have it being the bigger side over the smaller side. Okay, so for that last one, you wouldn't say the scale factor is 1 over 2 or 0.5, we'd say it was 2. Okay, so last thing before we move on and try some examples, just to confirm, if you're trying to show that two triangles are similar to each other, you just need to prove one of these two statements. Okay, if either one is true, it implies the other one's true as well. So if you have two pairs of corresponding angles and two triangles being the same, you can say the triangles are similar. Note that you only need to find that two pairs are going to be equal, because automatically that third one will be the same, because all the angles have to add to 180 degrees. Or if you can show that all three pairs of corresponding sides are proportional, you can show it's similar that way. So either one of these two, showing them individually, is enough to show that the two triangles are similar. Okay, enough of all that definition, all those definitions of mumbo jumbo. Let's try and do some examples here. So we've got two triangles here. First thing you always want to ask yourself before you even try to use some sort of proportionality or a scale factor is, you gotta confirm, are these similar? So looking over here, angle B and angle E are the same. We have the same indicator here. And angle A and angle E are the same, so these triangles are similar. So this means there's going to be a scale factor between these two. So you look for a pair of corresponding sides that we know. So over here, we know that side DF corresponds to side AC. So we can find our scale factor, and that's going to be, again, larger over smaller. It was going to be 12 over 3, which simplifies down, of course, to 4. Okay, so that scale factor, that relationship will be the same for every pair of corresponding sides. So if I want to look at these two sides, x and 5, that ratio between x and 5 will be the same as our scale factor of 4. So you can use that to write an equation. So this means that x over 5 is going to be equal to 4. And we can solve that equation by multiplying both sides by 5 to get a side length of 20. Similarly, we could do the same thing for these last set of corresponding sides, 8 and y. So let's use that in over here. So 8 over y, again, larger over smaller, is going to be equal to 4. This one might look a little bit trickier to solve because the unknown's in the denominator, but you can always get rid of that by multiplying both sides of the equation by y. So that'll give me 8 equals 4y. Divide both sides of the equation by 4, and you get y equals 2. Okay, so what I'd like you to do now, try this next example on your own first, and then push play when you're ready to see the answer. Okay, so hopefully you've tried B. What makes this one a little bit tricky is that we've oriented the triangles differently. We can still tell they're similar triangles because we have two angles being the same over here, another pair of angles being the same over here. So these are similar, but again, they're oriented differently, which can make it a little bit trickier to see which angles or sides correspond with each other. What you might find easier is to just rotate this triangle so it has the same orientation as the other one. Now my numbers have gone upside down here, but that's not too hard to fix. 5, 4, and 7. Okay, but again, now they're oriented the same way. It's a little bit easier to see what our corresponding sides are. So again, for my scale factor, look for that pair of corresponding sides that we know. I've got 6 and 4 over here. So my scale factor is going to be 6 over 4, which reduces to 3 over 2. Now I know this is equal to 1.5, and usually I have no problem with you using a decimal as long as it's an exact decimal. 1.5 is nice and exact. But if you get something like 7 over 6 where putting it into a decimal will be rounding, you don't want to do that. You're going to lose some accuracy. So I'm going to stick with using a fraction because there's nothing wrong with using fractions. We should become comfortable with using them. So I'm going to use a scale factor of 3 over 2 and know that that ratio should exist between all the pairs of corresponding sides. So looking at this pair over here, x and 5, x over 5 equals 3 over 2. Multiply both sides of the equation by 5. And when you do that multiplication, you should get 15 over 2 as the final answer, as I make room for that here. Okay, and last but not least, do the same thing for y. So we've got y and 7. So y over 7, same thing, same scale factor, 3 over 2. So when you solve for y by multiplying both sides by 7, you're going to get 21 over 2. Okay, and we've solved that one right there. Okay, moving on. 2 more examples here that again I'd like you to try on your own first. So pause the video, try them with a partner, and push play when you're ready to see the answers. Okay, so you may have found C here to be a little bit tricky. Again, these are similar triangles. We have triangle ADE and triangle ABC. They both share an angle at A, and you can use F pattern to see that the angle here at D and the angle here at B are going to be the same. So these are clearly going to be similar triangles. So let's look for our scale factor. Right here I have 9.8 and 3.7. So that'll be my scale factor, 9.8 divided by 3.7. Now, I personally don't like decimals inside fractions, so I'm just going to make my life a little bit easier and rewrite this as 98 over 37, just multiplying both top and bottom of that fraction by 10, just so I don't have any decimals inside fractions. And this, is again, ratio exists between every pair of corresponding sides. Now, where this gets a little bit tricky is figuring out what my lengths are for my larger triangle and for my smaller triangle. So for this larger triangle right here, I'm looking at this whole side length AB, and that distance, that length is going to be x plus 10. So my larger triangle has a side length of x plus 10. My smaller triangle, this one right here, side AD, has a side length of 10. So I have x plus 10 over 10 as my ratio there, and that's going to be equal to 98 over 37 for my scale factor. Okay, so it's a little bit trickier, a little bit weirder when you see the final equation, but just notice here that, again, this length right here, dB, is x, AD is 10, so together for that whole length it's going to be x plus 10. So what this means now to solve, it looks a little bit trickier, but again, it's not too bad. Let's get rid of that denominator first, multiply both sides of the equation by 10. So that's going to leave me with x plus 10 over here, as these 10s are going to cancel. And 10 times 98 over 37 multiplies the numerator, so you get 980 over 37. Okay, at this point now, all you need to do is to subtract 10 from both sides. So x is 980 over 37 minus 10. Okay, so find a common denominator, run that through your calculator, and you can figure out that that is going to be 610 over 37. Okay, so that'll be the value of that missing value x. Okay, so this is going to be continued in the next video, so we'll see you over there. Cheers.